So our last assignment this week is on multiple linear regression, and when you have continuous variables, and then obviously the same thing when you have categorical variables. I actually use two different data sets because if you look at the information Ken gives you, the data set on computer science and GPA, it only actually really contains continuous variables. It doesn't really contain variables that are categorical, so you can't use as an example for categorical data analysis as it pertains to regression. Anyways, if you look at the data set online, you'll notice that you have to use read_table2. This is because if you use read_table, things look strange. I'll just show you what it looks like. You won't be able to use data basically. You can see that it looks like this because if you look at the original text file, it's not actually spaced equally by one delimiter, so you can't use read_table. So you have to use two, and then it opens up things properly. Anyways, you guys know that when you run a regression model, you really should choose the variables that are most highly correlated. So this is why before you actually build the model, you should check to see the scatter plot. So I'm going to do that using ggplot. Yeah, so I'm going to do this using ggplot. Okay, so if you want to actually check whether or not high school GPA is correlated with university GPA, then of course you know to yourself that means that the Y variable is actually your university GPA, and then the X variable is whatever you think is going to be correlated with it. I'm going to first look at high school GPA because it's logical that like those who perform well in high school probably perform well in university. I'm wondering if I should put a line of best fit through it, but maybe, yeah. So I'm gonna put a smoothing trend to my plot in a bit, because sometimes you can't see things, especially if the relationship is not strong if you don't put a line of best fit there. So I'm going to do that. So I guess what I'll do is smooth. This is linear regression. So I'm going to use LM as the method. Okay, so what do we get here? This is actually okay. So this is what you get when you use high school GPA. So I'll just put P1 so we can look them together. I've worked with this data set a lot before with my third-year students. I can honestly say that you can't use all the variables in this model because they're too highly correlated. So the thing is that if for instance, verbal SAT and math SAT are pretty highly correlated with each other because they both correspond to SAT scores, you can't use them both. You have to use, and in fact, they kind of tell the same story. They're also very highly correlated with high school GPA. You will see that if you add too many of those variables to the model, your high school GPA coefficient will shrink because they're all too highly correlated. You can't just add things superfluously without checking to see why you're adding them. But I will make a plot, for example, for math verbal SAT. I'm not going to do them all. I'll just do math SAT scores so you can see what it looks like. And I'm going to put them in this. I'm going to put them in the same grid. So one thing I'm going to use the thing I used last week, which is grid extra, and I'm going to use grid the panel basically. Okay, so grid range. Use grid range. good range. Okay. Let's just put them on the same row. So I'll just do this. Oops. Oh, shoot. Why is there no points for the second model? Let me see, what did I do? Oh, I see why. It's because I forgot to put the points. Yeah, so you can see here that the first one is a relationship of high school GPA with university GPA. The second one is a relationship with math, SAT, and verbal SAT. Now, of course, we could add, math SAT. We could, of course, add the verbal SAT, but the reason why I chose math SAT is because they're computer science students. You might think their math aptitude is more important than their verbal skills in computer science, but just for, completion, we can put the scatter plot of, I don't know, the third one. I did something wrong here. Let me see. Oh. Oh, it's called verb SAT. That's fine. I chose a variable that doesn't exist. Okay. So if you run this, you'll see this. And I guess I should put 2 so it doesn't crowd each other. You get this. You can actually see that. I'll just put, I think I'll just put P3 by itself because it's a bit crowding. I'll do this. Yeah. If you look at the verbal SAT and math SAT, they look kind of remarkably similar. And if you look at the scatter plot of those two things together, you'll see that. So if you plot, for example, verbal SAT is a function of math SAT, you will see a very linear trend that is positive, suggesting that they're both pretty correlated. So they correlate with each other. So you probably can include them both in the model. I don't know if any of you have taken C67, which you'll notice that if you actually include both verbal SAT and math SAT, will actually shrink the covariance because they're just too correlated. So what you can see in general, basically, is that they're all 3 of those things exhibit a positive correlation because the trend, because the points, because as the X values increase, you can see the university GPA also increases. So this, but when I say the X values, I mean that it could be verbal SAT, it could be math SAT, and it could also be high school GPA, but you can see in all the graphs that there's something trending in the positive direction for all of them, basically. I should probably just make this like this. Yeah, now so usually when you have a very strong correlation, the points are kind of on the line. So I would probably say that, the points kind of trend on the line. I would say for high school GPA, it looks somewhat strong, but maybe for math SAT, for university GPA against math SAT and against verbal SAT, I might say it's moderate, just because you can see that the points are not necessarily trending so close to the line of best fit. It kind of moves a lot, off the line of best fit a bit. So maybe because you can still see the pattern, you can see the trend is positive, you might say it's moderate. If it was truly weak, you would probably not see any kind of trend at all that was positive. I'll just say like it looks, high school GPA against university GPA. The relationship appears at least moderate, perhaps strong, but for a verbal SAT, math SAT, it appears moderate. As the points don't necessarily exactly follow the line. Right, that's what you look for. So when you say something like the relationship is moderate, you should have a justification, and usually justification is that your points don't exactly follow the line of best fit. I guess I should say the line of best fit. Right, and you'll also notice for things that are kind of moderate in their association, it will kind of have a wide confidence band in the regions where you have low data points. You can see that the data points are kind of low. For lower GPA, there's more uncertainty as to why they performed poorly. Right, so for example, you can see the student here didn't do so well in high school, but did remarkably well in university. There's a lot of uncertainty for lower achieving students in high school. Whereas there's more confidence for those in university. I'm sorry, there's more confidence among those high achieving students in high school that their grades correlate to their university GPA. But when you look at, like, for instance, math SAT, you can see so that's why the confidence band is actually narrower here, yielding better estimates than it is down here. But you can see for math SAT, the confidence bands are kind of wide in general, just because there's more uncertainty as to whether or not math SAT is related to university GPA. We may not use that as the strongest predictor of our university GPA, right? It's not, doesn't appear to be a one-to-one fit there. Okay, so that's what I have here. So now we're gonna fit. So here we're gonna do a simple linear regression. So note that when you say fit a link, this is a simple linear regression. So I want to fit high school GPA against university GPA. This is a simple linear regression. So I'm going to call it model 1. Okay. So let's see what we get. So you can see here that if I were to actually write out this model, I would say that obviously, I would say the following. So let's just put the model here. The model is given by the following. So I'm going to use it. I'm going to use math mode here, I guess. 1.09. So this is the intercept term. 6.2. I'm not going to put all of them. 6.8, sorry. Plus 0.6748, right? So, and then I'm going to say times high GPA. Right, so this is what you actually have. Or I should say this times high GPA. So it's actually this. Yeah, it's so high GPA. So you can see that this is a positive relationship. It's also seen in your slope. That means, so how you interpret this is actually, I should really say the following. University GPA. And I guess I can actually just put this is equal to, I can put this like this, text. I'll just do the following. Actually, I can't actually. So let me just do the following. So I'm going to put y equals to your university GPA, but I want to just make sure, I want to make a notation here that this is actually an estimate. So I put a hat above because this is actually an estimate. So I cannot put y equal. It's not true. And I'll just put here that for y equals, for this hat of y, equals university GPA. Right, so it's actually an estimate. So you have to make sure you note that it's an estimate, right? And in fact, it's an estimate of the mean. So this is actually looking at like mean change in your high school GPA. So I need a glass of water. It's like really early in the morning for me, and I did not drink coffee. Okay, better. Okay, so what we can see here is that this is a mean estimate. This is an estimate of the mean change. Like I said last week, when you look at what you're actually looking at, you're looking at a distribution of possible values for y. So if you have something that looks like this, where you have, you know, x and y, and you have points. Technically speaking, this is a distribution of points. So if your point you actually observe is directly in the middle, but actually this is a distribution of points. So you see that there's a distribution on the values you actually observe. And so even though you observed one value of y, you recognize that if you take a different sample of size n, you can get a different y that sits along the distribution you see, right? So this is why when you look at your y hat, this is why when you look at y hat, when it's a mean estimate, right? Because when you take the expected value, so what you have is the following. You have a distribution on your yi. You have a distribution on your yi that's equal to beta naught plus beta 1, xi plus epsilon I. So if you take the expected value of this, right, this is actually, so what you're actually estimating is the following. You're estimating the expected value of yi equals beta naught plus beta 1 xi. So this thing here is actually estimating this thing here. You're estimating the mean change. That's because this is a distribution of yi's, and so you're not actually estimating yi itself. You're estimating the mean change, guys. So just be careful here. You're not estimating yi. You are estimating the mean change in a particular outcome. So this is something that we will check for your interpretation. I'm actually grading the last assignment, so I'm going to check this myself. If you say the mean change, if you say, for instance, the following, this is the change in. So if you say something like the following. For every unit increase in, you know, high school GPA, there is an increase in college GPA by a factor of 0.6748. That's not right. You know, you're not estimating y, you're estimating the mean change. Right, so you have to make sure you note this. It's the expected value of yi. You're trying to estimate the expected value of yi, not yi itself. So if you put change in college GPA without saying mean change, it's certainly speaking not correct. Right. So the other things I discussed last week as it pertains to significance, you can see that if we were to do a hypothesis test on this thing, it'd be largely significant because the p-value of this high school GPA, which is a slope term, is largely significant. You can actually estimate, you can actually compute this t-value, as I said last week. If you just take the ratio of the estimate itself, divide by the standard error, that's the 12.63 you see. And that's because the t-test itself, is actually beta 1 hat divided by s at beta 1 hat when you're trying to test significance. So that's why you see that you cannot, even though it gives you the actual t-value, you can actually compute it yourself as well if you just look at your statistics in the summary statistics, right? So you can actually compute this, you can actually figure out this test from this, but even though it gives you t, you can also find it because you have this and you also have this in your output. Okay. So two students, so this is that, I think this is part D. So it says 2 students have been admitted to university. One has a high school GPA of 3.0 and the other one has a GPA of 3.5. Obtain suitable intervals that summarize the GPAs each of these students might obtain in university. So this is actually telling you to find a confidence interval. So you're being asked here. Find a confidence interval based on their scores. I think there's a function called predict. I want to put in, so I want to see if I can do the following. So x is equal to see if I want to put two, I want to make a vector that just takes, so rather than actually trying to make predictions at all the particular values, I only want to make them at 2. That is 3.0 and 3.5. So I want to see if I can do a prediction based on just, just the 2 values. So you're being asked to make a computer confidence interval. And so you have to use a predict function. But the thing is, you already have your model, so you can do that basically. Yeah. Let me see here. Because if I put predict model, it will give me the prediction of all the things, of all of the categories, which I don't necessarily want. Right, so if I do this, it'll give me every single prediction for all the different estimates. I only want 3.0 and 3.5, so I need to find a way. So just give me 1 second. I'm just going to look online. Prediction for point in GLM. I don't want to predict everything. You see that here, we feed the model in, it'll give you a prediction for all 100. There's 105 observations and it'll predict all of them. But I don't want that. I only want them for 2, basically. Yeah. Yeah, I think it might be predict LM. So let me see. Yeah. It's actually this. So I need to give new data. So x equals. So data equals tibble. I'll explain what I'm doing. I just want to see if it works, and I'll explain what I'm doing in a second. So data, see if it works. No, it's still giving me too many observations. And I only want 2 observations. For some reason, it's giving me more than 2. Yeah. Yeah, for some reason, it's giving me more than I actually wanted. So let me see. Data is, yeah, it's 2 points. I don't know why it's predicting. Okay. I'll figure it out. Where you troubleshoot in R while you're teaching. No, this is not what I want. What I really want is, so sorry, maybe I should explain what I'm doing. So what I'm doing here is I'm trying to create a data frame that is new data so that I can actually predict just the data itself. But when I give model 1, for some reason, it predicts everything, which I don't want. I only want to predict those 2 points. So I need to figure out why it's not doing what I want it to do. So I need to figure out why exactly it's doing that. I don't know why it's doing this. Should not actually give me. I hate all these ads for boot camps. This is just okay. I know I've done it myself. I just don't remember how I did it. I'll have to come back to this. So I really want to create a prediction interval. Maybe I'll just see if my data. Let me see. I only want to predict 2 points, but if I put the model inside without specifying a data to actually make a prediction on, it will predict on everything. I don't want 105 observations. I just want 2 predictions, but maybe if I do predict.lm, let me see. Let's see what it does. So yeah, it does the same thing. So if I look at the dimension of predict, yeah, it gives me everything. So it's not doing what I wanted to do. I'll have to come back to this. Maybe, if anything, I'll probably figure out if it's like a tutorial. So what I want to do, I'll just make a note here what I want to do. The predict thing actually gives you a way to find, the prediction gives you a way to find, so if I do something like the following, I can actually find confidence intervals for every single thing here. Yeah, so I actually put, I did put X, but it doesn't, so it doesn't, I don't know if a work is X. To my knowledge, I think you need to put a data frame. Let me see. Yeah, it doesn't work. So it doesn't take a list. The reason why, so just that's an important moment I had here. The reason why I put I converted X into a data is because predict doesn't actually take it. You have to put a data frame basically, and it recognizes X as a list, so it won't actually run, right? So if you put model 1 X, it won't run because it recognizes X as a list, but it's looking for a data frame. This is why I put tibble of X, so that it would recognize that it's actually a data frame, not a list. And so when I put in X, so I don't know if that will work because tibble and data frame are the same basically. So it's most likely not going to run. You can see the same issue. It's the same issue. So even if I put predict, it's the same thing, right? So it doesn't predict. Predict is for a broader class of things. LM is, I can put predict works for like survival, GLM, different models, whereas predict.lm only works for linear regression. Predict itself, so predict works for a broader class of functions. Models, right? But the LM only works for LM functions. But yeah, so just to be clear, data frame and tibble are doing the same thing for the most part. So what doesn't work for tibble won't work for data frame either. So the problem is that it's not actually that I called it tibble. The problem is that it sees that I only gave 2 data points to predict on, but the model itself is asking for, the model itself has 105 observations. So I think what I have to do actually is I need to figure out, I need to put something else here. I cannot put a model 1. I need to specify which particular points I want the model to estimate on. So let me see. I wonder if, I have an idea. I wonder if anyone actually scored a GPA of 3.0. I don't think they did. I'll figure this out later on. So I will come back to this. So what I really want to do is make a confidence interval. I can't right now because I haven't figured out my code. I will figure this out in the next tutorial. So when you look online, when you rewatch the video, you'll see it. But yeah, just to clarify, the problem wasn't actually that I gave it a tibble, because a tibble and data frame are doing the same thing in R. The problem is that the model itself has 105 different predictions, but I only asked for 2, so it doesn't like that. So I have to figure that out a bit, and I will get back to you guys on that. Okay, so now I'm going to do, so this is MLR. So I'm going to get back to this because obviously I know how to do this. I'm having a brain fart. It's a little bit early for me, but I'll come back to this. Okay, so now we're doing MLR, and you will see that when you include more things in your model, you have to check what happens to the thing to check for is the standard errors. So, because sometimes it tells you if things are going wrong. So if I add in everything, so high school GPA plus, let's say, verbal SAT plus math SAT, you'll see that you'll see that the standard errors actually increases for the high school GPA. And now you can see that so before, notice that the standard error was, the t-value was 12 point something, now it's 6.4. That's because the standard error actually increased, because it's too correlated with these 2 things. Notice that while this is still significant, the high school GPA, the significance was actually diminished when you added verbal SAT and math SAT, because they are themselves highly correlated with high school GPA. So you actually shrunk the effect of high school GPA by adding 2 variables that are not significant, but are correlated to it, right? So if you look at, for example, the pairs plot, I don't know if he's ever showed you that. If you look at the pairs plot, I just want to see if I can do this here, and just for curiosity. Let's look at the pair plot. So pairs plot. So pairs let's say, if you look at the Paris plot of this thing, you'll see they're all pretty highly correlated. So these are the predictive variables. These are the Paris plot for the predictive variables. You can see they're all pretty highly correlated with each other. That's the problem, right? So while rural SAT and math SAT are not necessarily very significantly predictive for university GPA, you can see the p-values are not significant on those two things. They're not highly predictive of university GPA. There are two highly correlated with high school GPA, so that actually shrinks the effect you see on high school GPA because of that strong correlation. So you actually should not include them all in the model because of this multicollinearity you have between your predictive variables, where they're all pretty positively correlated to each other. So based on this, you might say that the two SAT scores has not improved the model. I'm going to give you several reasons why. One, it shrinks the effect. I'll tell you what I think is important, but I'll tell you what he wants to see. It shrinks the effect of the significant covariate, which is high school GPA. But there's a couple other things. You know, what he wants to see, so the good answer you probably want to see is that if you perform a hypothesis test, and you should on both, being, you know, i.e. verbal SAT and math SAT, you will see that none of them are actually significant. So go through the formal process of doing a hypothesis test. You can see the p-values for both are greater than 0.05, so you wouldn't call them significant. But the other thing is that you can actually check and see other diagnostic things. Like if you look at the F statistic from the original model, notice the F statistic is 159.6. The F statistic is actually shrunk to 55.7. Right? So that, you know, the F test actually shrunk, the F statistic shrunk. So the global significance is also lowered by adding two insignificant covariate. Those are three things that they're kind of telltale signs. That kind of tell you when you messed up a bit, right? You added covariates are not good in your model. That's when you have a bit of an issue, right? So those are three things that kind of tell you maybe you made a mistake and you added covariates you should not have added to your model. There's more things I could say, but I won't because I want to get to categorical variables. But that's three things to check for when you add covariates to your model. I'm going to not do these things just now because I don't have time and I want to show you categorical, but there's a code most likely in the lectures where you can perform backwards elimination. I don't even know if he taught this, so it might not even be appropriate to cover this right now. He probably didn't cover backwards elimination, so I'm going to omit this. I don't think he necessarily covered backwards elimination just yet. I'm not going to cover it myself. Instead, I'm going to move to categorical variables. I'm going to go back to the empty cars. And I'm going to look at the only relevant categorical variable they have in the data set. So if you remember empty cars, let's look at empty cars. Let's look at empty cars. I'm going to just pull the data set up. Empty cars. So it's this data set here. You will see that they have this variable is categorical. It appears like it's not, but it is, because 4, 6, and 8 corresponds to how many cylinders you have in your car. Where you can imagine that the weight of the car is probably like highly correlated with like how many cylinders you have, where 8 is probably the biggest car because it has so many cylinders. You might imagine that with weight, you will see a downward trend with MPG. And so that means that cylinder itself might actually result in a situation where the MPG is actually lower for heavier cars, basically. So let's see what we get. So you get this. This is probably not the best thing to do. This is me actually plotting the weights of the cars across the different things. You can see that the weights of the cars don't actually overlap. The miles per gallon doesn't actually overlap between the different weights. You can see it's down for the heaviest car. This is probably not very good. I probably should use a box plot. So if I just do a box plot instead, I might get something that's a bit better. But you can see even with the points that the MPG is actually the highest for the lightest cars. You can travel faster with lighter cars. But anyways, use an appropriate graph like this. You will see that there's quite a bit of spread across the different distributions. So we could question whether or not we should be actually assuming equal variance. But anyway, I digress. You can see that there's really no overlap in the different weight classes. There's an outlier here and a lower one over here, but for the most part, their medians don't actually overlap. So you might think that the cylinder class is significant covariate. So why am I doing this? It's because I want to see if cylinder class is potentially a significant covariate. And if I can partition my MPG into different cylinder classes, it might indicate that when I put this in the model, it will come up as important, basically. But notice that because 4, 6, and 8 are numerical values, I have to actually use as dot factors, so they recognize them as factor levels and not numerical values. That's why you see 4, 6, and 8 like this. So let's look and see what we get. So let's look at the model of cylinder class. I'm going to remove this. No. So maybe I think that, for example, so perhaps I think that the MPG, like the miles per gallon, is related to how heavy a car is. This may result in my using cylinder and weight for obvious reasons. They both, in some sense, are proxies for how big the car is. I put them in the model. What do I get? You get this weird thing that happens here. So you get an estimate for weight, sure, but you get this weird thing here where you can see that you're missing a cylinder class 4. Does anyone know where the cylinder class of 4 went? Because like you see the estimate for 6 and 8, but where is 4? Does anyone know where 4 is? In this cylinder class? It's somewhere, but where is it? So it's actually in the intercept term, basically. It's the reference group. Did he cover reference groups in class yet? Yes or no? Let me know if he covered it. So I'm guessing he didn't then. So whenever you have a discrete variable, technically speaking, your reference group is the intercept term itself. So which means that when you look at the estimate for 6 and 8, it actually corresponds to the mean change in your MPG as you go from weight class 4 to 6. And as you go to weight class 4 to 8 is this one. So you can see that when your car is heavier, they both decrease. And so you can see that the extent to which it decreases is actually more for weight class 8 because it's heavier than 6, but they both decrease because Of course, 4 is the lightest group. So if it's in the intercept term, you can imagine the change from 4 to 6 would be negative, and the change from, of course, 4 to 8 is also negative. And they're both pretty significant. You can see from the p-value, they're both pretty significant, as is weight. The only thing I would kind of think about basically is you can imagine that weight itself is probably kind of correlated with, or at least associated with, the cylinder class. So again, so based on this, we can see that weight and cylinder class are both significant. The p-values for both are less than 0.05. But I just want to check something. I want to check to see, however, I will check to see how weight is related to cylinder class. Because even though they're both significant, we could have the same problem we had over here, where it appears right, like the pairs product are all kind of correlated. So the problem with it, because it's categorical, we can't use the scatter plot in the same way. Instead, what we should probably do is look and see what we get by the box plot, like see if there's a split. So I'm going to put here weight. So yeah, you can see that even for, there's some kind of association between weight and cylinder class. It appears like they're kind of, there's an intersection there in the sense that like as the weight class increases, sorry, as your cylinder class increases, your weight increases. Technically speaking, whenever you have, I'll just put as a note here, when you have two variables that are, potentially associated, that one is categorical, you may think to perform a chi-square test of independence. That's really to ensure that you don't have two variables that are kind of saying the same thing in your model, because then you might just be better off with using one or the other. But anyways, it's just a demonstration, so we're not going to get that into things. But anyways, you might ask, what is the association? What is the interpretation of the categorical coefficient? Because you actually don't see 4 in the output, it's actually the reference group, which is the intercept term itself. So what you're actually seeing is a change. You go from 4 to 6, and then obviously from 4 to 8. I'll just put here from group 4, from class 4, right? So it is a change you get when you move from class 4 to 6 or class 6 to 8. That's how you interpret it. And I should really say it's the mean change, basically. Right, it's the mean change. So when you interpret the coefficient, you have to do it from the perspective of the cylinder class. So that's why you see that you have to interpret in terms of like the change you get when the mean change you see in the MPG when you move from like 4 to 6 or 6 to, or like, 4 to 8, right? So it has to be done within the scope of, it has been within the scope of going from 4 to 8 or 4 to 6, but the interpretation is kind of the same. When you want to form significance, it's as it always was, right? You still have to do beta 1 equals 0, except now you actually have 2. Here you have to the coefficients, the level 6 and 8. If one of them was significant, the other one was not, there's implications there. You might think to absorb what the non-significant one into the intercept term. and then just keep the one that's significant. So they might not all levels are significant. So this is why you perform the test separately. If there used to be a version of the course where you had to do a project at the end, where you do a project to determine like what the best model is for your data. I don't think you have it in this course. I think it's already have a final exam, and the course is a bit changed. When I took the course, I used to do a final project as well as a final exam, a midterm, and a set of assignments. But I think they changed it because it just was a lot for students. But in theory, if you found out that, for example, you had if you found out you had one level was significant, the other one was not, you need to recenter your variable or redistribute your variable to make it look a bit more in tune with the fact that not all the levels are significant. But I don't think that will come up since this comes up in this course, because I don't think there's a project. So probably the full extent of what you'd actually see in your assignment would be the testing for significance of the different levels. So I guess I will stop here, and I'm going to just have a coffee. And I didn't figure out this thing here, the confidence interval, but I'll figure it out in the next tutorial. Then when you watch the video, you'll see it. And also it will be in the code when I post it on my GitHub. So eventually I'll fix this, and then you will find a confidence interval, because that probably is on your assignment. So I'll figure this out in the next 10 minutes, and I'll update my GitHub code. But that's it. Have a good morning. So last class, I was actually confused about something pertaining to the confidence interval. I figured out this tutorial, so I'm going to just go over it in careful detail when I get to that point in time, because the other students didn't actually get, there was something with my code that was a bit wrong, but I figured it out during break. Anyways, this is based on a couple of things. One data set I use quite a lot actually, but you can see that when Ken gave you a link to the data set, it doesn't display the data very well if you use read table. That's because if you look at the data set itself, it's not actually, it's not spaced by one delimiter. So I'll show you what I mean by that. You get something else like this, where the values don't situate themselves under the actual columns adequately, and then there's not an exact space between each particular value. So if you try to use read underscore table, it won't actually load your data in an appropriate way. So instead, you have to use read underscore table 2. That actually does give you a data frame looks like this in R, which is what you actually want. Anyways, this is data on 100, I think it's on a community college for 105 different students. They're computer science students. So if you look at the data frame, you have a couple of things. You have high school GPA, you have math, SAT, verbal SAT, computer GPA, and university GPA. So what they're particularly interested in is how the high school GPA, as well as math, SAT, and verbal SAT, in some sense predicts your university GPA. Like, are those people who are students who perform well in high school, they consistently perform well in university, and like, they want to know which factors might predict your performance in university. So I always tell people before they actually make a model, never to just make a model. You have to look at your scatter plot first. That's because it's entirely possible you find two things are related to each other, but not in a linear way. So you need to apply another model. So the first thing to, in any kind of regression setting, is first to actually look what you have in your data. So I made a couple of plots. The variables we're interested in here is obviously university GPA, but then also high school GPA, math, SAT, and verbal SAT. Like, are all these three things significant in predicting university GPA? It turns out, if you look at the plot, you will find that you will see that the actual plot for, one second, please. Sorry. Okay, so if you look at the actual scatter plot, you'll see that there's actually three. There's one for high school GPA, one for university GPA, and one for SATs. Actually, you could have put them all in the same thing, but I thought it looked kind of bad. So in theory, you could have done the following, I guess. Maybe just change number of rows to 2 or something. I didn't think it displayed very nicely, but it's up to you, I guess. But if you look at it, you'll see the actual best relationship is actually with high school GPA and university GPA. If you look at math SAT and verbal SAT, you'll actually see that while there is a positive trend, it's sort of funky over here. And really over here, you see that there's quite a big spread of the points. So it's kind of hard to determine how good those two things are going to predict, university GPA. So keep this in mind. Probably your best predictor is high school GPA. You're asked here to describe any relationship you see in your scatter plot. Its direction, its strength, and its shape. Please state all those 3 things in your answer. I'm actually grading this myself, and if there's something missing, you won't get full marks, right? So generally speaking, if you think there's a positive relationship, you should state why. Really, for a positive relationship, you should see an increase in, I guess in this case here, either your high school GPA or your verbal SAT scores or your math SAT scores is associated with a positive and like an increase in your actual university GPA. Otherwise, if it's negative, you'd see the opposite thing. So please state this. I think that the relationship with high school GPA is at least kind of moderate, especially because you can see over here, the points are pretty good, pretty well trended. And if I pull it up here, I just put this in the thing here, you'll actually see, well, it doesn't do a great job over here, which is why the confidence band is kind of wide. It does a pretty good job over here at predicting. So I think it's at least moderate, but you might not think the same of, like, for instance, you might not think the same of high school GPA, sorry, you might not think the same of math SAT scores. You can see that the points are visibly off the line and the confidence bands are kind of wide everywhere, merely because it doesn't do a great job at fitting the data points since they're quite spread. I think the same thing is shown in verbal SAT. And university GPA, you can see the same distance from the point and the line. So that might indicate that it's at best moderate, but you can still see it's positive. So there's still some kind of increasing trend, albeit kind of moderate because the points don't sit directly on the line. So I might say that it's kind of moderate, sort of looks linear, maybe not that strong. But anyways, the reason we're doing this is because you can imagine that you should not plot a line of best fit on variables that are not significant. So you have to see those things before you actually plot them. Yeah, so you're asking this question here, which I think is actually D, to fit a linear regression. This is a simple linear regression, similar to last week. The reason we choose high school GPA is because it's the strongest one. And you can see from the scatter plot, it has the best relationship, just double check and see. Yeah, you see it is visibly, you can see from the graph, it does the best job thus far at predicting high school GPA, college GPA. So if we're just interested in, for instance, a simple linear regression, we might choose the high school GPA. So let's go see what we get. I told the last students that it's really important how you interpret this thing. And I think I kind of lost my graph. I told them that, technically speaking, what you actually have is for every value x, you have a distribution on y. So if yi is distributed normal, with the actual distribution come from the error terms itself. So the error terms are distributed normal with a mean 0 and a variance of like sigma squared. You can see that if you have a line that looks like, if this is your line of best fit and you have points on this line of best fit, technically speaking, these points sit on a distribution. So it's kind of like you saw one glimpse of the data, but you could have seen multiple versions of the data, right? And different versions of the data will have different values of y, but those values of y will sit on this distribution of possible scores, is what it's really saying. So it sits on the distribution of scores that look like this, right? And so technically speaking, when you take what the fitted value, what this is actually computing here, this is not actually computing this. It's actually computing the expected value of this. So it's actually an expected value. So the expected value of the yi is where it sits on average, right? It sits on average, it sits in the middle of the distribution, sort of maybe here. So you're actually computing this. You're not actually estimating this, you're estimating this, which means that when you're looking at your response, when you're trying to make sense of your responses, you have to make note that it's actually a mean change. It's not actually the change in Y, it's a mean change. Right, so I specify the model based on the covariates here. You can see that it's given by 1.0968 is your intercept term, plus this is a slope term, which you can see is positive because we can see from the graph the relationship between X and Y itself is also positive. So you expect a positive relationship, obviously for the two variables. So you can see I kind of wrote, yeah, so here it is. I'll show you my code. I put it in math node, but sometimes math node is icky. Yeah. It's giving me grief this morning. Well, yeah, there you go. You can see it looks like this. I put Y hat, but I did indicate here that Y hat's university GPA. It's just I wanted you guys to know that it's not actually, you're not directly estimating university GPA, you're estimating the mean change in university GPA. So that's why I put hat, so you know that it's not actually, it's not Y itself, it's not university GPA, you're estimating the mean change in the expected value. And in fact, it's the case that, you know, note that it's actually the case that hat, this thing here, is an unbiased estimator of the expected value of yi. So you're not actually computing yi, it's actually the change in yi you're looking at, the mean change. All right, so this is an important thing to note. So you don't, so this is why am I saying this is because if the interpretation is the following. Whenever you have an increase in high school GPA, there's an increase in the mean change of college GPA by a factor of 0.6748. If you put the following, an increase in the change, it's actually not right. And I'm going to look for those things when I'm marking your tutorial worksheets. And if I see something like the following, the mean change, or if I see something like the following, the change in college GPA without the word mean, it will not receive full marks, so it's not correct. So just want to make sure that this is clear. So make sure you're specifying, you know, that it's the mean change, not the change itself. You're not estimating Y, you're estimating the expected value of Y. Okay, now it says this is where I messed up last tutorial. So it was 2 students were admitted. So 2 students were admitted with a high school GPA of 3.0 and 3.5 respectively. Then it said obtain suitable estimates for their GPA so they might receive in universities. When it says obtain suitable intervals, they're actually saying find the confidence interval. Where I made a mistake last tutorial was that I actually forgot to specify that it was, so I put X, I put something like X here instead of high school GPA, and it doesn't recognize X in the model because I put high school GPA, so it doesn't recognize X. That's why it wouldn't run basically. You have to make sure when you create a new data frame that the labels of the variables are consistent with the labels you put in your original model, right? So this is a common mistake that can happen. Don't put any arbitrary label. Make sure the labels are consistent with the labels you use in your original LM model. Because I use high GPA in my LM model, I need to specify data frame that maintained the same variable label, but I instead put X and didn't recognize what X was, which is why it wasn't able to run properly. I want to create a prediction interval. Actually, it's really a confidence interval based. So somewhere in the data frame, you'll see somebody had a GPA of 3.0 and 3.5. So I'm going to use a predict function to create a confidence interval. I should really call it confidence. Right, I should call confidence. Because a confidence interval and a prediction interval are not the same thing. So you're looking for a confidence interval, basically, that kind of is supposed to make sense of where their scores happens to be. Okay, so I put a data frame. You can see that when I just run this point here, it's gonna be a data frame with just 2 values because I'm only wanting to make an interval for 3.0 and 3.5. Oh, sorry, I forgot the N. Okay, so new data is actually just a data frame with two values basically. Predict is actually a really flexible function because it takes multiple models. You can put a linear model. I think you can put survival and multiple different models inside this thing that would specify different confidence intervals for different models you're using, different GLM models. Okay, so I want to find usually generally speaking, if you're not given an alpha level, assume it's 0.05, right? So I'll make a note of this. If not given an alpha level, assume that it is 0.05. So this is why I have a 95% confidence interval, right? It is actually a 1 minus alpha percent interval. 1 minus alpha. One minus alpha percent interval. Right, that's what it is. So this is 95%. So let's run this and see what we get. You see you get this. So what you have is your actual estimate is the fit itself. So it estimated a college GPA of 3.12 with a lower limit of 3. I guess if you round 3.07 and an upper limit of 3.18. And then for the other one, because there's a positive trend, we expect that somebody who had a higher score in undergrad, or sorry, a higher score in I guess high school would have a higher score in undergrad. So you can see that their estimate is actually 3.56 if you round, with a lower limit of 3.39 and an upper one of 3.52. So we expect this to be, in some sense, making sense. So what does it mean? It means if you take many samples, size 105, I guess, you expect that 95% of the time, your actual parameter for their actual GPA you observe for these students who had a high school GPA of 3.0 and 3.5 just sit in these intervals, basically. So you intuitively expect the interval to be bigger. You expect the interval to sort of be contain larger numbers when somebody performed better in high school because it's a positive relationship. So yeah, this is where I messed up again, just to reiterate so you don't make the same mistake I did, is I forgot that in my actual model, my variable was not X, it was high school GPA. But then when I was actually making the actual data frame here, I put X. The other thing to make sure you're being careful of is you cannot put a list in here. So if you don't create a data frame and you just put, if you do the following and you put like, new data equals C of, let's say, or if you do the following, if you do high school GPA is equal to C of, let's say, 3.0, 3.5, and you put this into here, it won't actually run. It doesn't recognize lists. You have to put a data frame for it to make the predictions on. So this is why I actually put data.frame of high school GPA. It won't actually recognize just the actual list itself. And in fact, if you try to put in the list itself, it will just say we don't recognize the list and won't actually run anything. Okay, so this is your prediction. So this is, if you're asked to make a suitable interval, that is essentially what you're being asked. You're being asked to find a confidence interval, and here it is. Okay. Now I'm going to add 2 covariates to the model. Keep in mind that these covariates weren't actually necessarily very significant. If you looked at the original plot, you saw that high school GPA was certainly far superior and like tracking university GPA. But if we add these 2 things to the model, you can see that something is funny, right? So if you look at the original model, you actually see that standard error for the estimate was pretty high. It was like 12.632 with a low p-value. And that is because if you look at your actual if you look at your t-distribution, you can actually note that when your absolute value of t is large, you have a small p-value, right? That's because they're in the tail. It's either over here or here, right? So when the absolute value of t is large, you're going to notice your probability of seeing such a test statistic like that is unusual. So what it's saying is that the chance of seeing your test statistic, which is t is equal to, you know, the point estimate itself divided by the standard error, the chance of seeing this so extreme in the tails, if the null is true, because it's a distribution on the null, basically, right? This distribution on the null, it's the null distribution. So it's saying that the chance of seeing such an extreme observation, if the null is true, is unlikely. So you get a small p-value with it, right? So keep this in mind, a small p-value is associated with a very large quantile, 12.632. On the other hand, when you add the two covariates to the model that we know are like somewhat less significant, see how the standard error for the high school GPA actually increases to 0.085. And as a consequence, when you take the ratio of this thing divided by this, it actually shrunk. Instead, it went from 12.6 to 6.4. And because your test statistic is now somewhere back here, so it was 12.6 here, now it's like 6.4. You can see the p-value is actually larger as a consequence because the area above it is higher. You can see that the probability of seeing such a test statistic increases. It's actually, you've actually made your high school GPA less significant when you added these two covariates. You can also see it in the F statistic because the global F, which is the F statistic for the entire model, went from 159.6 to 55.7, which means that if you look at the distribution of the F's, the global F, it also is itself has a lower p-value, right? So here the p-value is 2.26, which is the same thing here. However, if you plot it, you see it looks like the following. Everything went from like 159.6, seems like 55.7. So you see the p-value is actually higher. It's just that because you get rounding, it doesn't tell you what the exact p-value is in R, but it's certainly less significant because you added two covariates that are not as significant, because you can see neither of them are themselves very significant. So you added covariates that actually shrunk the effect of your main significant predictive variable, but did not actually contribute much to the overall model. There's a reason why. It's because if you look at the relationship between high school GPA and verbal SAT scores and math SAT scores, you might think that somebody who performed well in high school might also perform well in standardized tests. I mean, I have some thoughts about that, but let's suppose that's what it is. Let's suppose your high school GPA is, you know, like related to your performance in your standardized tests. And you might think that they're kind of correlated. People that did better in high school might have higher standardized test scores. Those things are correlated with each other. And when you include covariates that are highly correlated into your model, the consequence is that they all shrink in the effect, right? So unfortunately, if you add variables that are all correlated to each other, it actually reduces the significance of each of the covariates individually. And you can actually see that all the variables themselves are pretty highly correlated. They all exhibit a positive, they're all increasing positively together, and you can see a linear line emerge, right? So I put a Paris plot on all the different predictive variables. You can see that they all are trending in such a way that you see a very positive trend emerge. So which means that high school GPA is positively associated with verbal SAT scores. It's also positively associated with math SAT scores. And also you can see that math SAT scores is positively correlated with, you can see verbal SAT as well. They're all highly correlated, which is pretty problematic as it pertains to trying to put together a model that is actually significant. So we probably shouldn't include them all together, basically. But anyways, when the question here asks, test whether the two scores has actually improved your model. So this is actually E. There's a couple of ways you could do this. So really the good answer is this. It's number 2. I put good answer as number 2 because when he says test whether the adding two covariates has improved your model, he's actually telling you to perform a hypothesis test. So generally speaking, he's asking you to do 2. So if you want to determine whether it's, you know, the good additions to the model, generally speaking, what he's asking you to do is to perform a hypothesis test, and you would see that both of them are not significant to the model when you look at the hypothesis test. But I think there are a couple of things you could also note in this model, which is that you can see that it shrunk the effect of the significant covariate, which is high school GPA, and then also the global laugh is also lowered. So if you're to perform a hypothesis test on the overall model, you might say it's significant because the p-value is still low at 55.77. You can still see p-value is very small, but it's significantly lower in terms of how small it is. So you can see that in multiple ways, adding those two covariates to the model did not enhance your model. But what he really wants you to say in E, what he says test, he wants you to do too. But I'm just making you aware that in fact there's multiple things that went wrong when you added those two covariates to your model. Okay, I don't think you guys learned backwards elimination just yet. So I actually did not do the last two questions in the chapter 19 for this data set, just because I think it would be confusing to introduce things you didn't learn. I'm going to switch gears to categorical variables, which you do see this week. I'm going to use my faithful data set of like empty cars. I'm very keen on this data set. And the reason why I like it is because you can see that it has this nice categorical variable here, cylinder class, which you might imagine is probably related to weight, because cars that are heavier might have more cylinders. And it's also related to MPG in the sense that heavier cars probably are slower per gallon. So you might imagine there's a negative association between cylinder class and MPG in the sense that you'll notice that as the cylinder class is increasing, your MPG is probably going down, which is what I want to show in the plot. So if I want to look at the association between a continuous variable, which is MPG, and something that's categorical, you cannot actually use scatter plot, because even though you can see, even though cylinder is 486, it's actually a factor variable that has 3 different levels. So you cannot use a scatter plot. And in fact, if you do use a scatter plot, you will see a very weird thing happen. So I'll just kind of show you what happens if you don't use a scatter plot, thinking that it's something that is actually continuous. You will get something funny. So if we run this, we will get this, right? Which kind of shows you that it's really not actually something that's continuous. You would see it from the plot, it's a discrete thing. If you try to use a scatter pairs plot, if you try to use a scatter plot, you will see that it doesn't make sense because it's a factor variable, right? So I'll just put a note here. If you use a scatter plot, it looks odd, right? So here we will use a box plot because we can see it's categorical, and that will give us some insight into the relationship. You get this, you can actually see that there's something to be said about the cylinder class, in that as the cylinder class goes from 4 to 6 and then 4 to 8, you can see that the MPG goes down because your car is slower when it's heavier, basically. There's obviously 2 outliers here, but outliers aside, you can see that the medians don't actually overlap at all in any of the distributions. They're all pretty spread apart. Okay, so if I think that MPG is in some sense related to how heavy a car is, I might think to use cylinder and weight. And you can imagine that weight itself probably, if you look at the plot of weight, you can check and see, you'll probably see that if you look at the plot of weight against MPG, you will see that it itself is probably actually also you have exhibit a downward trend. So I'm just going to show this here. You can see it looks like this. So similarly, you could always, and obviously we can put a line of best fit. You can see that there's obviously a negative association where the heavier cars move slower, right? That's not a surprise. And we see the same thing with cylinder class, because cylinder class and weight are kind of related to each other in that way. Oops, I'm going to say LM. So you get this. It does a little poorly here because there's not enough data points, but it does really well in the middle here. So you can see that where those data are sparse, it doesn't do amazingly, but for the most part, it does a pretty good job. Okay. So let's look at our model of those two things. You can see that a couple of things. You get that weight is certainly significant. Notice that it's actually negative, right? Which is because it's a negative. So what you actually have is the following. You have the following thing here where your t-value is over here, and that's still significant because this is a two-sided task. We're asking the following task, beta 1 equals 0. Beta 1 is not equal to 0. So even though it's negative, it's negative 4 point something, it's still a significant result basically, right? It's just over here in the far end. That's because it's a negative thing. So when you take t is equal to beta 1 hat divided by s of beta 1 hat, and your beta 1 is itself negative, you'll get a negative t statistic. That's still significant, but on the other end of the distribution, right? And in fact, you're going to get negative t-values for all of them for the same reason. All of the slope covariates are negative, but we know that t is equal to beta I hat divided by s of beta I hat. So if your coefficient is negative, your t-test will be negative. But this is a two-sided task. So anyways, inevitably significance can occur at either end of the tails. You can see here that the as dot factor for cylinder class 4 is missing. This is because it was actually absorbed as the intercept. So you can see that if this is kind of a funny thing, because if you were to write this out, you wouldn't include as dot factor 4. You probably put something like the following. Beta 1, sorry, you put y I hat is equal to beta naught plus beta weight, I guess, times weight, right? Plus beta hat, you probably put, I'll just put 6 for cylinder class 6 times cylinder, right? Equal cylinder 6, right? So the cylinder equals 6. So plus beta 8 hat, I'll put cylinder equals 8. Generally speaking, you actually have two indicator variables here. When I say cylinder 6, I really mean 1 if it's 6, 1 if cylinder equals 6, 0 otherwise. And the same thing is true here. You have another indicator variable where it's 1 if your cylinder is 8, 0 otherwise. Which means that, for example, if you have a cylinder class of 8, you put 1 here, this ends up being 0, and you just have this plus this plus this. If you want, on the other hand, if this is actually, if you have, for example, 6, and this would be 1, this is 0, you would have these 3 things, right? So that's how you actually interpret the model. And, if you're working in the class of, and that means you can see that indicates that the reference group here, which is absorbed in the coefficient itself, is cylinder class of 4, basically. Right? So what you're looking at here is the mean change in the MPG as you go from cylinder class 4 to 6, and the mean change in the MPG as you go from cylinder class 4 to 8. That's what you're seeing in these two coefficients here. They are both significant, which kind of makes sense because if you look at the actual plot here, you can see that the medians don't overlap. So we kind of suspected that perhaps we'd see a significant effect. Now, the only thing you might wonder to yourself is like, is it possible that, and so I'll just make a note here that, I'll make a note here that when you see a reference group is 4, you have to interpret every interpretation within the comparison of any reference group to 4. Yeah, so how you interpret this, Eddie, is that you would say that, so I will make the following interpretation. The mean change from going from, let's say, cylinder class 4 to 6 is a change in the MPG by negative 4.2556. And there's a mean change in when you go from cylinder class 4 to 8, negative 6.0709. So both of them are significant, but the p-values for both of them are significant. Now it's possible that when you get your assignment, that not all the levels are, it's possible when you get your assignment, when you look at the discrete variable, some of the levels are not significant. You would see that in your model because one of the levels you would have here would have a p-value that's bigger than 0.05. That's possible to have too. When you get that, that's a bit tricky because you could imagine that you may want to actually recombine your variable in a way that you only kept the significant thing. So if, for instance, I had found that cylinder class 6 was not significant, then I might make a new variable called cylinder 2, where cylinder 2 contains only 2 levels, 4 and 6 together, and then 8 by itself, right? So if I found that some of the levels were not significant, I might create a new variable called cylinder 2, where I put 4 and 6 together and 8 by itself. But in this case, it's not necessary because it turns out both groups are significant. But if you saw in your assignment, for instance, that one group was not significant, one thing you might do is just combine the two groups that are not significant together, and then create a new variable that just only has a 2-level system or something. So you don't pass into the model insignificant covariates into your thing, basically, right? Now, to interpret this in such a way that, so interpreting categorical variables are a bit strange, because you have this thing here, where you have 2 different estimates for different levels of your covariates. So this is because you have to make the interpretation within the comparison of the reference group 4. Notice how I said going from group 4 to 6 and 4 to 8, because the reference group itself, which is the intercept term, is actually 4. This is why it's not expressed here in the model. You just see 6 and 8, you don't see 4, because it's the actual, it's the intercept term, basically, right? So you have to explain what you see in your estimate in the context of the reference group, which is group 4, right? So you can see you have a decrease in the MPG when you move from cylinders 6 and 8 from class 4 base. So it essentially means if you change from class 4 to 6 or from class 4 to 8, you see the mean change given by those estimates. You have to make this comparison in comparison with the reference group in mind, basically, right? But because you can see when I actually partitioned my covariates into a model, I actually split them into 2 different covariates. When you perform the hypothesis test, it's the same as you always did in the context of continuous things. However, now you need to actually do the following. You would actually have 2 tests to perform for the different levels. So let's, like this would be one variable here. Right, you essentially would have two tests you're performing, basically, right? Where this is, maybe this is, maybe this is like, this is this, and this is that. You essentially have to do 2 different tests, but the test as it always was, is just now you have to do tests on different levels of that variable, basically. So does anyone have any questions? So there's no questions. I guess we can end a little early today. I'm going to post this on my GitHub, like this lecture, and then I'm also going to post the YouTube when it gets to my email, like when it renders. I'll post it on my YouTube, then you can watch it again when you're last, because I think this is the last assignment. I think your last assignment A, which might be posted this week. So I will make sure this is posted in a timely manner so you can watch it before you do your assignment. But otherwise, have a good morning, everyone. I'm going to stop here.